Thank you so much for coming. My goal is to help data engineers get a better feeling of what deep learning is, and the feeling is that it's really quite simple. So how many data engineers are there in the room? Please raise your hand. How many data scientists? Okay. Nice. I wonder, like only half of the people raised their hands actually. I wonder what would be the other 50%. So I'm a PhD in speech biometrics. I've been in data science field for about 15 years, and I'm with Data Monsters. We are doing custom data projects with great customers and partners. If we're talking about deep learning, it's very, very simple. It's basically referring to artificial neural networks that contain more than one hidden layer. If you see a network with two hidden layers represented by the green dots here, it's basically a deep neural network. Nothing else in it. But there is a lot of interesting stuff around it. Deep learning was found to outperform traditional machine learning on large amounts of training data for different modalities: images, text, sound, and time series. And this caused a lot of excitement around deep learning. And you would know that deep learning requires a lot of compute power because it's a lot of matrix multiplications, basically. This is how you can depict where deep learning fits into the whole picture of machine learning and artificial intelligence. Some people confuse deep learning and think that it's kind of similar to AI, but actually AI would be represented by this larger circle and would include anything that helps people to be more efficient or productive in the work. Rule-based systems, knowledge-based systems, knowledge bases, sorry. And it goes inside with machine learning, the classical one, which would include things like linear regression or decision trees. And then deep learning is here inside. Why machine learning is different from rule-based systems? The main difference is that machine learning uses implicit rules. It is capable of building its own rules based on samples of data. You present a set of samples to the machine, to the algorithm, and it is capable of training itself to make predictions for new samples that it hasn't seen before. And it is powerful because it can be very flexible. It does not depend on an engineer to create those rules and to maintain them, updating for every new business situation. So machine learning is one step above rule-based systems. And deep learning is even more powerful. I will explain why. The classic machine learning tasks would be these ones. To classify, predict a class of an object, like is this a spam email or not spam based on email body? Is it a man or a woman on the website now based on their behavior, activity? So it's one or the other or several classes. Classification. Regression is predicting a value for a continuous variable, like what would be your sales next month? What will be the house price on Zillow, for example, based on location and other parameters. And they do not use photos of the houses yet, but that can be a good prediction factor. Anything else in this category? And also clusterization, grouping similar objects without being explicitly told what to group by. You just tell the machine, I want to efficiently target my users, and I'm ready to split them into 10 different segments, and we'll see what their actual features are. how they are different. So you can give the number of segments, and the machine will split the entire database of users by similarity between those users. You don't have to explicitly tell the machine, this is the user belonging to cluster 1, this is cluster 2. It figures out that on its own. And also ranking and recommendations, sorting the data to maximize a value function like click probability or request relevance, and recommendations. What movies would the user like based on the behavior of other users that look kind of like this one. And classic machine learning is very dependent on the features that you select. Like you would want an expert to explicitly tell the machine for the user behavior or for the house price, you need to look at the zip code, at the footage of the house, etc. You need to explicitly provide the machine with the parameters that may be important. The machine will be able to create a box, an equation that would combine those parameters and help you predict something on the data. And the features can be extracted straight away, like age, price, number of purchases from the data set. They can be invented based on the domain intuition by the experts. For example, what the customer churn relates to. And this can be the number of support requests. Or we know that the money behaves like a logarithmic value, and we need to log the money if we are making predictions on sales. For more complex objects like images and sounds, for many years, scientists have been creating specific features to that domain, like SIFT or HOG or MFCC for speech, mild frequency capsular coefficients for speech recognition. Some of these features are patented, and they are served to train a machine learning model. A lot of efforts of engineers was spent to come up with these features to train a machine learning algorithm, a model. In deep learning, it's different. A machine learning model which is using deep neural networks is able to figure out what features the model needs to care about automatically on its own. And the features are oftentimes better than the manual engineered features, those that I've mentioned before. For example, there is a class of neural networks called convolutional neural networks. They learn hierarchical features from images. Like they understand that these shapes, these transitions between colors are important to classify dogs from cats, for example. So as an engineer, as a scientist, you don't have to invest your time in inventing these features. The network will be able to do it on its own. And this is very powerful. This is what makes deep learning very different from classic machine learning. So we can depict, again, these 4 categories like that. Rule-based systems, they go from input through hand-designed rules to an output. Like, is this fraud or not fraud, based on the number of transactions from different countries, for example. For classic machine learning, the system will need these hand-designed features to then be fed into a machine learning model that will train itself to predict the outputs. For deep learning, it comes up with hierarchical features that then are used to train a deeper model and to predict the outputs. So it is called end-to-end learning. You get from pixels to categories for images, like for example. And this was revolutionary with deep learning. The deep learning is a game changer in many use cases because it can provide higher quality. It can help the data science team to iterate faster, sometimes with less investment. As I was saying, it can use raw data as inputs, pixels, sonograms, words, characters, whatever. And this is opposed to some cases where creating the features is extremely complicated. And you cannot use some of those created features because they're patented. And it gets you directly from end to end, from pixels to a category, from sonogram to characters, like Baidu speech recognition did. Or for translation, German text, English text to German. And that means it can be less data preparation and labeling. The AI history actually began 72 years ago in 1943, when McCulloch-Pitts introduced binary threshold neurons, and then Hebb learning. Hebb researched how the neurons is adapted inside our brains during the learning process. Then 1950, Marvin Minsky and Dean Edmonds, they've built the first neural network with 40 neurons, artificial neurons. And then Alan Turing with his famous test and other brilliant ideas, like reinforcement learning. So the approach is quite aged. Something has changed since then. Now that we're able to use these neural networks in a new way. And also the algorithms have been around for 30 years or so. Like backpropagation was formulated in 1970. The CNNs, convolutional neural networks, were invented in 1980. RNNs, LSTMs, CTC, the connectionist temporal classification, which is very popular now. It was all invented a while ago. The difference, and there is quite a history for neural networks and different approaches to solving these problems. The AI has been seeing a lot of ups and downs, and now we're kind of in an overhyped state of the market and of the industry. But as you would remember, many years ago, like 1956, John McCarthy said, we think that a significant advance can be made if more, in one or more of these problems, if a carefully selected group of scientists work on it together for a summer. Or 1965, machines will be capable within 20 years of doing any work that a man can do. So we did not see that. That resulted in AI winters, several AI winters throughout the last years. I believe we might see a new AI winter now. We need to be very careful about our promises, what AI can do and cannot actually do. AI meaning deep learning in this case. But a lot of people are attracted to this field, and that inspires a lot. The difference is that the large data sets became available approximately after 2001. And throughout the whole history of computer science, people have been focusing on algorithms. And now we have seen that having more data can be even more powerful than creating a very efficient algorithm. This table shows that the availability of the algorithm on the right side stands like 18 years apart from a major breakthrough in this area, while the data set is only 3 years before a breakthrough appeared. So data appear to be really, really important for many of these breakthroughs. For example, in speech recognition, the technologies that used classic machine learning, hidden Markov models and Gaussian mixture models were not very good at using lots of training hours of data. While with deep learning, the difference from small training set to a larger data set, training set was significant. So we have found that data is important for deep learning to be efficient. This is a recent study by Google. They've trained a deep learning model on their scale using 300 million images fed into the machine learning model, and they have found that the mean average precision was growing with the increase of the data amount in the data set, which means, and there is no plateauing, nothing like saying that we'll get to a limit somewhere. So we need more images to be very efficient with computer vision. And that's why Google allows you to upload your photos in Google Photos for free with no limits. I would say this use case, this article in 2011 was the first significant breakthrough for deep learning. And this one was with road signs. At that time, deep learning, a committee of convolutional neural networks performed better than humans at recognizing what road sign is this in the picture. And that was incredible. Nobody expected that we will get there that soon. So it was 2 times better than humans with the error rate of 0 to 0.54% error rate. The next one was in 2 years later, recognizing house numbers on Google Street View maps. Humans did 2% error rate, the machine was 9.94%. And then the ImageNet contest. 1 million images, human performance was at about 4%, and in 2015, the researchers came up with quite a complicated neural network with 152 layers that outperformed humans in this task. And that was one of major breakthroughs. So these are some of the examples that of the images, of classes of images that the neural network was able to recognize. So I'm saying that I would not be able to ever recognize these 3 images. I don't know what kind of dog it is, but the neural network was trained on it and was efficient. Some of the mistakes that it made, the GT stands for ground truth, the real label given to the image by a labeler, human. And we can see that, it actually looks kind of similar to what the machine came up with. Acoustic guitar, altar, wine bottle instead of restaurant, like we were expecting to see restaurant as the tag. But there is actually a wine bottle. Something in these areas is also very, very credible. Plate, meatloaf, ice cream, kind of ice cream, yeah. So we have seen that the machines are quite powerful there. Lots of data and new architectures of neural networks. We have also seen that they can be easily cheated in some cases. For example, this image of panda, if you are able to engineer the noise that you would add to this image with a very, very small weight, which visually results in an image absolutely similar to a human eye, would trick the machine in giving a completely different label to it. So we need to be very conscious about using machine learning and deep learning for predicting things. And there is a big movement in in this area. Like, what should we entrust to the machines, etc. So these are the three things that make deep learning very successful: the deep neural networks, the new ways to combine mathematical entities together, availability of huge amounts of data, and the compute power, the GPUs. So this is an example of how more data and more compute power made a jump from the LearnNet case, which was trained on 2 to the power of 7 pixels with this many transistors. And in 2012, AlexNet was using much more pixels and much more transistors to be trained. And we can still compare it to the human brain. AlexNet was less than 1 million units, and human has 100 billion neurons. So I think we have not reached the limits of these algorithms. The important thing was that in 2010, in Switzerland, they've issued a paper finding that training neural networks on GPUs gave a speed up of about 50 times, 50-fold speed up. And this is because GPUs can perform a lot of computations in parallel, because they have thousands of cores. In comparison, CPUs have like a very finite number of it, like 8. So deep learning has a lot of matrix multiplications inside of it, and GPUs were designed to do that very operation. So NVIDIA is now very happy because they can serve a whole new market need, whole new market segment with their GPUs built for a different goal. And well, many players are trying to catch up, but it's challenging. We can see, this is a slide from NVIDIA GPU Tech Conference from last May. GPU compute performance is growing 50% per year, CPUs only 10%, because GPUs can leverage those parallel computations much more efficiently. So NVIDIA is in a very good position, and we are as well. Now we can leverage GPUs to do a lot of computations for deep learning and get to very interesting results. Some of the tasks that deep learning was strong in are speech, images, and video. For example, classification and localization. What do we see on an image and where the object is located, the boundary is bounding box of an image. And with a lot of data, neural networks outperform humans for these tasks. And also, NNs do semantic segmentation, pixel perfect segmentation, meaning which pixel on an image belongs to a specific category. This is broccoli, this is a road sign, this is a car, this is a pedestrian. Then style transfer, making your pictures look like an artwork, an art piece. Image generation, and robot perception. Emerging area, I would say, is text and NLP, natural language processing. And we have seen word embeddings and different language models to recognize speech from audio to text. Then sequence-to-sequence learning for machine translation. And also the things that is emerging now is question answering and dialogue systems and text generation. These last two are not solved yet. It would be exciting to see this solved. And also reinforcement learning robots, games like you've seen Atari Go and Dota 2 recently, and AlphaGo 0. And the things that I think we would be seeing soon is combining several modalities, for example, images and text, doing image captioning, for example, or searching the web by image, and we can do it already. Video descriptions, like translating a sequence of images into text, what is happening in an image. That would be very useful for security purposes, for example. Visual question answering in an image. Given an image, the machine should answer to a question formulated as text. Speech recognition from video, that enhancement by articulation of a person in the video, and many other things, like extracting depth from an RGB image. Well, I think we can expect a common representation for several modalities. Embeddings not only for words, but also for images or for thought vectors, so that we could be using similar algorithms to train the machine to understand the world and make predictions on the world in general, not only on a narrow task of problems. And we are also seeing that convolutional neural networks that were created initially for images are now used for text, and vice versa. RNNs created for time series and text work well on images, for example, on videos. So this transfer of ideas between domains is very powerful. One of the new challenges with deep learning and neural networks is that instead of engineering the features, you now have to engineer the architecture of these neural networks. Creating the right architecture will help the network to be efficient for a specific task or a set of problems. So people are creating all kinds of architectures for the neural networks, and they look beautifully and differently. If at your company you will be thinking of starting into deep learning, you may encounter some barriers to entry. You will need lots of data, like 1,000 data samples per class for images, lots of compute power. The more power you have, the faster you can iterate on your models and tasks. And you will need expertise in deep learning, deep neural network architectures, because it can be important in many cases. And some of the my advice would be to overcome potentially those barriers by using transfer learning, because it means that a system, a neural network, can be trained on another data set, on another set of images, and then you will apply that pre-trained network partially to your data set, your categories. Like you need to recognize one competing brand versus the other competing brand, and you do not have hundreds of thousands of samples of that kind of products. You can train your neural network on another data set, publicly available, and transfer learning will help you solve it for your specific case. And also, many data sets are publicly available. There are marketplaces for data sets. You can acquire some of those from different vendors. And you can collect your data and hire a company to label the data for you, because deep learning, is typically trained on labeled data in most cases. The need for lots of compute power also can be tackled by using transfer learning, and also if you do not have a need to run a lot of computations continuously, you can just rent a GPU in the cloud. And 2 weeks ago, NVIDIA and AWS have announced the availability of their NVIDIA's new GPUs, Voltas, in the cloud, their top line of GPUs. So this is really powerful. And overcoming the lack of expertise in deep neural networks can be also easy in specific cases. Many real-world tasks can be solved using standard architectures. Well, and if you have lots and lots of compute power. You can, Google had shown that you can replace expertise in deep learning with a machine that will be finding the optimal configuration of the neural network to train itself, instead of having a data scientist do that. A little bit on how it works inside. So it was inspired by the neurons in the brain. And a neuron has dendrites. The input signals that come into a cell body get translated into an output signal somehow, and then go through the axon to be transmitted to potentially other neurons or muscles. So this is a simplified model that helps us understand what's important. In the reality, it's a little bit more complicated, but we can forget about it for now and try to be simple, to keep it simple. So we model the neuron in the brain by collecting the inputs, like an axon from another neuron comes in, and this is the feature that we observe in the world. And we have several features, x0, x sub 1, x sub 2 coming in, and we apply a weight. We just multiply the input value by the weight that we'll have to learn somehow. We combine it, we sum it together, as simple as this. And we add some bias here, can be just one, to put it together like this, and we apply an activation function to this value. So it's just a sum of weighted inputs and a function to calculate the output. So the output axon is the value of that function. And there are different activation functions. For example, this is the sigmoid function. It goes from 0 in here in minus infinity to 1 somewhere here. And it equals to 0.5 in the middle. And there are different ones, like that binary threshold neuron 72 years ago is like this. There are also all kinds of activation functions invented and tried by humans. Why do we do this? Because we want to find an efficient configuration for a specific task. So one of the important elements of the architecture for neural networks is having the right activation function for neurons. So we have the hidden layer, so-called hidden layer for a neural network. We have a set of inputs, the observed features of a neural network, and we have the output layer. Just the terms that are typically used here. And it works like this. If you have several layers, it's just as simple as with one neuron. But instead of getting the output right from this neuron here, you get this output and use it as an input to the next layer. So all the artificial neurons on the previous layer get connected to the next layer, and so on and so forth. So the output function here will be the sum of inputs at this level before the output layer of the neural network. And there is a very efficient technique that made deep learning possible. It's called forward propagation and backward propagation. It allows us to learn these weights that we use to calculate the activation function from the examples. For a specific data sample that we have observed, we based on the weights that we came up with. Maybe initially it can be just a random set of weights. We measure the distance between the output that we have calculated with our weights and the desired result. Like we wanted the house price to be predicted as 1,000, we got 100. So we would use that delta, and we will propagate it back and update all the weights of the neural network so that the next time the network is given this example, it will get closer to the desired result. And there also third important element is the loss function. How you measure the distance between the desired outcome and what you actually observe. It can be very efficient. Well, a specific loss function can help you get to the result much more efficiently. It has been found that creating deep networks where all the neurons are connected to the previous layer is inefficient, and the networks with 3 layers are typically, well, 4 and so on, do not get you any performance boost in accuracy. So other types of neural networks have been created, like convolutional neural networks. It basically calculates a weighted sum from pixels of an image, and it uses this matrix to calculate the activation function for every neuron on the next layer. So instead of 100 weights, it just uses 9 weights for a 3x3 cube to calculate the entire next layer. And it comes up with different features. For example, for an image of a cat, it shows some activations on different layers which seem quite random, but the patterns it's looking for, these are weight functions for these matrices that the network comes up with. They seem to be meaningful. And CNN solve object classification, object detection, semantic segmentation, and are used for self-driving cars. There is another kind of neural network that has a notion of time. The neurons, the artificial neurons on the hidden layer get connected to the neurons on the next time step within the same layer. And you can unfold the recurrent neural network like this. So you have an activation function at this time step, and this function gets inputted in this the same layer on the next time step. And the recurrent neural networks are good at dealing with time series. But they have a problem of vanishing gradients. So the network in its outputs tend to forget about what happened some time ago. And to solve that, Jürgen Schmidhuber came up with the concept of LSTM, a network that keeps its internal state with the ability to remember it when needed, when something important occurs. And it has so-called write gate to write down a new value for this internal state. So this is the forget gate, forget. So it zeroes out some of the values of internal state. This is the write to update the state, and this is the output gate. So it changes zeros, ones, and in between to modify the state and output the values. It solved the problem of vanishing gradients. And some of the use cases for neural networks were like this. Given a set of phrases, the network can reply to a question, where is the apple, after some movements happening to the apple, or what kind of tree is in the background. given an image. Machine translation is getting to the perfect level in many languages because of bidirectional LSTMs. This is an example of machine creating a caption for an image group of people shopping at an outdoor market. And image colorization, coming up with a color for the pixels in a black and white image, trained on previous images. AlphaGo, self-driving cars, dense captioning, what's happening in an image with a very high detail level, making photos look like Van Gogh pictures, coming up with new volcanoes or new kinds of birds based on description. This bird is completely red, etc. And robots. I would not be seeing this. And some of, well, I guess I do not have time, but some of the industrial use cases are really inspiring. Like this one in sports. Track players or create automated video highlights in tennis or something like that. So the conclusion is that we can think of deep learning as of automation on steroids. If you have a lot of data and the accuracy for your use case is critical, you should be looking at deep learning. And the more compute power you have, the more ideas you can test and faster you can iterate. And in this slide deck, I have a set of links that you can use to dive deeper from like self-teaching part to following the thought leaders, etc. And please email me for the slide deck, alex@datamonsters.com. Thank you.
A huge amount of data about deep learning. If there are any questions, we still have a few minutes because our next talk is
I'm fascinated by the adversarial thing with the pandas, right? And so, from the human eye, you actually can't see the. However, apparently there's some very subtle. Okay, what would happen if you took a picture of the adversarial panda and then plugged that in? Would it be a panda?
Yes. So that's a good way to augment the data set. Like you try to trick the system, and you use that new data sample to train the system and say, no, that's a panda. So this is another way to get more training data by using pictures that look similar to a human, but would improve the performance of a machine. However, it will be still possible to come up with an adversarial example, even if you do a lot of those artificial samples.
Yeah, so for a lot of the text-based, input to neural nets, they used to use word2vec to convert words to sort of the vector space,
Right.
but it seems like it's going away from that to just straight characters. Are there still cases where like using word2vec makes sense?
Definitely, yes. Well, word2vec is one of the techniques that made embeddings of words very efficient. There are others. They can account for different other aspects of the words, not only taking care of the neighborhood of a word, but also some aspects related to the meaning of the word. And also the words can be misspelled, and also there can be new words combined from separate pieces of words, like those suffixes less, ness. So there are approaches that take those n-grams of characters into account, and they augment word2vec techniques to account for unknown words as well. And there are studies on that.
Okay. If there aren't any more questions, why don't we thank Alex?
Thank you.